Hello, everyone. My name is Doughty, and today I'm going to be really briefly talking about two different topics. So the first is the potential use of metal absorption studies to better understand the timing of reionization, in particular focusing on studies of neutral oxygen. And the second is the effects of binary stars on galaxies and gas during reionization. So measurements of the electron scattering optical depth have indicated that reionization is close to halfway finished at a redshift of 8, and measurements or inferences of the H1 neutral fraction and alpha opacity suggest that it's probably finished closer to redshift of 6. However, there's difficulty in determining the H1 neutral fraction through direct measurements because of the high H1 column densities. And as has been mentioned several times already, there's evidence of substantial amounts of neutral hydrogen at lower redshifts. So clearly some lines of sight remain quite neutral even at much later times. So taking these into account, people have been interested in complementary ways of studying reionization and studying the timing of reionization. And a number of studies have suggested the use of metal absorption lines with transitions redward of the Lyman limit to better understand the ionization state of the IGM during the Epoch of Reionization. So with this in mind, we ask, how can metals, in particular neutral oxygen, which has a very similar ionization energy to hydrogen, be used to constrain the timing of reionization? Some other uncertainties about reionization are centered on the galaxies and the stellar populations. The intrinsic emissivities of galaxies at that time are not directly observable, but are inferred from other measurements, for example, of the ultraviolet luminosity function. And this is usually used in tandem with assumptions about the stellar populations at the time. In particular, assuming that the stars are primarily single stars. However, some studies of low redshift galaxies have determined that, particularly for massive stars, the majority of stars can be in binary or more stellar systems, as you can see here in these blue lines markers. So it's worth considering the possibility that Epoch of Reionization galaxies also contain large binary fractions. And some works, for example, in 2016, have already looked at this sort of thing, incorporating binary stars, and have found, for example, that binary stars can result in an elevated escape fraction for galaxies during reionization. So we ask here, if we assume that galaxies during that time period had a high binary fraction, what are the effects of those binary star populations on galaxies and their gas? So to address these questions, we use SPH cosmological simulations that are based on the Gadget 3 code. These simulations include on-the-fly multi-frequency radiative transfer over dozens of different frequencies. So because so many frequencies are included in the radiative transfer calculations, it can better model the photon energies that are going to affect metal transitions, which is what we're interested in. And then enrichment of the metals is modeled self-consistently according to prescriptions for evolved stars and different kinds of supernovae. And you can see these papers for more details about the simulation. So we also have interest, though, in making comparisons to observations, metal absorption studies. And so we have artificial quasar lines of sight probing the simulation volume. And from these lines of sight, we generate fake spectra using the apparent optical depth method. And this process is intended, as I said, to mimic the observational method of using quasar absorption spectra to look for the presence of metals. And these spectra have artificial noise added, and we end up with a catalog of absorption systems for a number of common metal transitions. So turning to the first topic that I mentioned earlier, keep messing this up. We examined the incidence rate of neutral oxygen absorption systems in the simulation. And you can see that here in these dashed lines. So we wanted to know, can the incidence rate of oxygen 1 tell us anything about the timing of reionization? You can see the simulated incidence rate for weak absorption systems in oxygen 1 right here. And there's a drop in the incidence rate that corresponds pretty well with the end of the late stages of H1 reionization. And you can see here the solid line plots the H1 neutral fraction in the simulation. And the incidence rate drops when the neutral fraction is roughly 1%, which has been identified in some simulations as the epoch of overlap. So you can see that the incidence rate in the simulation occurs earlier than in these observations taken from Becker et al. 2019. The simulation may also be producing sort of an earlier reionization compared to the inferences that are coming from observations. But from this, we would say that the H1 neutral fraction volume weighted probably is reaching about 1% when you see the drop in the observations. We also wanted to see if the neutral oxygen fraction could be used to directly infer what the neutral hydrogen fraction would be. However, when we examined this, the ratio had a very scattered relationship, which didn't seem to hold much predictive power, and also wasn't as useful, perhaps observationally, because it would require photoionization modeling to determine what all of the different states of oxygen are. However, if you switch metrics and use a ratio of co-moving densities of neutral oxygen to silicon, which is another alpha element, and look at the gas in detected absorption systems, there's a very linear relationship between these two quantities. And this H1 neutral fraction in absorption systems very well matches the mass-weighted H1 neutral fraction. So if the scaling of this relationship could be better determined with modeling, this could be useful for learning more about the ionization state of hydrogen. The relationship doesn't hold as well when you're looking at basically the volume-weighted neutral hydrogen fraction. So regarding the second topic that I mentioned, I would be talking about the effects of binary stars. We run two different simulations with different versions of the binary population and spectral synthesis, SPS models described in Eldridge et al. 2017, and one with single stars and one with binary stars. So on the left here, you can see a spectral energy distribution of a model stellar population, one with single stars, one with binary stars. These are normalized at 1500 angstroms. And you can see that for a wavelength above the Lyman limit, the amplitudes of these are very, very similar, virtually identical. However, for lower values, the amplitude is higher for the binary star spectra. So the spectrum is harder for a binary population. And when these models are ingested into the simulation, you see it results in an elevated photoionization rate in this top panel for the simulation containing binary stars. And it means that hydrogen reionization completes sooner by about 75 million years. And this result is qualitatively also supported by results from Rosedal 2018, who did a very similar experiment here using multi-frequency radiative transfer, although with fewer frequencies. We then examined star formation and gas properties in the two simulations. So first of all, the star formation rate density in the simulation decreases when we include the binary stars. You could see it really sort of ramp up after redshift of 6. If we examine directly the traits in the temperatures of the CGM and the IGM, where they're defined according to some overdensity cutoffs, when we examine the temperature and the intensity, which are these solid lines, there's not too much difference between the two models, but there is an elevated temperature in the CGM gas indicated by these dashed lines in the simulation with binary stars. So it's heating up some of the gas. And then by a redshift of 5, we see that there are minor increases in the stellar and ISM metallicities in the simulation with binary stars, about 7% and 15% respectively, although the overall enriched gas mass in the binary star simulation is lower. So effectively, there's less enriched gas, but it has more metals in it. So we interpret that as that accretion is somehow being halted by the gas heating. The last thing I wanted to mention is that when we look at the metal absorption systems, they seem to jive very well with the rest of the picture that we're seeing, which is that the harder ionizing background associated with the binary stars results in fewer and weaker metal, low ionization metal absorption systems like the O1 and silicon-2, for example, and boosts the number and abundance of high ionization metals like silicon-4 and carbon-4. So binary stars could potentially affect the observable distribution of equivalent widths in these metals. So I'm over time, so I'll just leave you with my takeaways. Thank you.
All right, thank you, Kathleen. So time for questions. Right, so there's a question from the Yongda Zhu. The question is that it is interesting that the density ratio, O1 over silicon, can linearly trace the neutral fraction near absorbers. What's the physics behind that?
We our thinking behind this, using this ratio, was that the overall justification for using O1 again in this study is that it has an identical ionization energy to the H1. And so it would be in charge exchange equilibrium with neutral hydrogen, and the neutral fractions of those two elements are linearly related to one another, at least for certain physical conditions. As I said, this sort of deviated when we actually looked at it in a simulation, which I would anticipate means that the physical conditions weren't right for that to be true. So replacing neutral oxygen to total neutral oxygen in basically the neutral oxygen to total oxygen fraction, the neutral fraction ratio, using silicon instead of oxygen, we chose that because it's an alpha element and that the abundance should change relatively similarly to the oxygen, so it should be produced at similar rates, relatively speaking. So that's kind of the justification for that choice.
All right. So there's another question from the Thomsons. How does the IGM temperature compare between BPAS and Hart and Maddow models?
I don't remember exactly what the Hart and Maddow models would predict for the IGM temperature. I know that because this simulation has radiative transfer, the background, in certain areas, the background ends up being harder, and in other locations, it's spatially fluctuating because of radiative transfer. But I believe that sort of thing is not supposed to, that's not really what varies the temperature at the mean density, at least that's my understanding. So I'm not 100% certain how it compares to that prediction.
Okay, all right. So are there any more questions from the audience? Okay, yeah, there's another question from Sultan Hassan. If reionization happens earlier than binary stars are increasing the ionizing photons and hence star formation rate at high redshift, and you show that binary stars suppress the star formation rate at low redshift, why would binary stars behave differently as a function redshift?
Why would they behave differently as a function of redshift? So at least as far for regarding the star formation rate density, I hope I'm not misunderstanding your question. My interpretation of that is that the binary stars contributed to an earlier reionization, and so earlier heating of some of the gas, the IGM and also the CGM, more so the CGM, and that contributed to a reduction in accretion and possibly a reduction that the reduction in the formation rate was based in no longer accreting as much gas. So it's possible that maybe there would be a drop in the single star model that went to lower redshifts. I'm not 100% certain how those things are sort of interacting. But we could talk about it later.